guessed it, we're doing message digests. A message digest is basically a one-way hash function that takes an arbitrarily long piece of plain text, and from it, it computes a fixed length bit string. So basically, a message digest is a hash function that you can apply to any arbitrary message. And when you apply it, you're going to output a hash, and that hash is always going to be the exact same length, and it's going to uniquely identify that message. So that way you can authenticate the message by looking at the hash associated with it. Message digests actually have a couple advantages over signatures. The first is that message digests don't actually couple authentication and secrecy. They only focus on authentication, and this is useful when you don't really want or need to keep a message secret. Why would you want to do this? Well, when you use message digest, there's no need to encrypt the entire message. You only have to apply the hash function to the message to see if the message hash matches the hash you were given. And this is much faster than encryption, as we can see by point 3. Message digests actually come with a couple properties. The first of which is that if you're given a message, you can always compute the hash by just applying the message digest to the message. But according to property number 2, if you're given the hash, you cannot easily find the message by applying the function to the hash. It's a one-way hash. You can only use the hash function on the message to obtain the hash, not vice versa. Property 3 shows us that 2 distinct and unique messages will always have unique hashes associated with them. So whenever you apply the hash function to a message, you're always going to get a distinct and unique hash. And this is important so that we can associate one hash with one message. And then finally, the final property of it is a change to even one input bit produces a very different output. So if I even change one word in the message, I'm going to get a completely mangled hash, and this is good for security reasons. Message digests can also be used to speed up signatures. This is useful because instead of encrypting the entire message over again, you can just encrypt the hash. That way it is much quicker because the hashes are typically only about 128 bits long versus a message that can be any arbitrary length from very small to very large. So it makes it run much faster. And that was with symmetric digital signatures. This is with public key signatures, and it works the same way. You can also speed those up by just encrypting the hash. Next, we're going to talk about one very popular hash function, and that is the SHA1 algorithm. SHA1 stands for Secure Hash Algorithm 1. So that's what we're going to be going over. And the way it works, so we're just going to go through the processes. Before you start the algorithm, you're going to first initialize H0 through H4, which can be found right here. And those are going to be initialized to a constant, and they're going to be specified by the standard. The reason for this is because you want H0 through H4 to be consistent every time that you start the algorithm. If they're inconsistent, you're going to get a different hash every time you apply the algorithm, and that is not a good idea. After you have initialized H0 through H4, you're going to split the entire message up into 512-bit blocks, and then you're going to process them each in turn, as we can see by number 2 here. So you're going to send one 512-bit block of the message through the SHA1 algorithm, and then you're going to basically update W, which in turn will update H. At the end of that cycle, W is going to be reset, and you process another block, and that's basically how SHA1 works. All right, next we're going to look at MD5. MD5 was developed by Ronald Rivest. MD5 also uses the sign function, and it also gives us a 128-bit hash as an output. And SHA1 also gives us a 128-bit hash. MD5 has actually been found, has actually been considered broken, as collisions can commonly be found in MD5, which means that it's very hard to authenticate messages in MD5 because many people can basically break it. However, it's still a popular message digest for no known reasons. With Message Digest, there is a way to target communication when people are using Message Digest, and the most common way is a birthday attack. A birthday attack is an attack derived from the birthday problem, and it's used to interfere with communication, basically. So like I said, birthday attacks are derived from the birthday problem. And the birthday problem poses the question, how many people do you need in a room before the probability of having 2 people with the same birthday exceeds 50%? Most people would assume that it's going to be upwards of 180, more like 183, because that's just above the amount of days in a year, which is 365. But in reality, it's only 23 people. So only 23 people need to be in a room for the probability of 2 people to share a birthday to be above 50%. This answer can be arrived at by looking at the equation below. It mostly involves some fancy mathematics and a sprinkle of magic, so we'll just leave it at that. But as you can see, when we show 23 people, when we add 23 people to the room, we have about a 50.7% chance that 2 people will share a birthday. With that knowledge, we're going to revisit birthday attacks, and from that we can deduce that based on the inputs and outputs, N and K, we can always define, or we can always know the amount of pairs that can be made, which is always going to be N times N minus 1 divided by 2 input pairs. From that, we can actually determine that if the number of inputs is greater than the square root of the outputs, we have a very high probability to find a match. From that, we can deduce that a 64-bit message digest is actually very likely to be broken by only needing to generate 2 to the 32 messages. While this seems like a lot, in actuality, it can be broken rather quickly, especially with faster processors nowadays. All right, next we're going to talk about the management of public keys. So there are a couple of problems with public keys that we do need to address. The first problem is that obtaining someone's public key for the first time is mostly insecure, as there's no way to encrypt your messages without someone else's public key. The second problem is that public keys can only be used to verify identity. They're not very useful in identifying or verifying attributes of a person. For example, if I wanted to show that I was over the age of 18 or that I was a citizen of the United States, I couldn't use public keys to do that. I'd need something else, which we're going to talk about. And then the final problem occurs when we try to fix the first problem. If we were to have a key distribution center to safely distribute keys, that could cause a problem as well, because if the KDC or key distribution center were ever to go offline, we would have no way to authenticate keys or distribute them, and that would cause internet security to be basically non-existent until it came back online. So how do we solve these problems? Well, the answer is certificates. Certificates are designed to bind a public key to the name of a principal. A principal can be anything, a person, an organization, a company, even a dog if you wanted it to be. Just any entity that you can attach a public key to. Certificates are always distributed by a CA. A CA is a certification authority, or certificate authority. And they distribute the certificates, and they always sign it with their private key so you know that it's authentic. Certificates are like a driver's license. They're not very secret and they're not private. They're used to show your identity or to verify you. So just like you would show a driver's license to a cop to show that you're above the age of 18 or that you can operate a motor vehicle, you would show a certificate to other people that you're conferencing with in order to demonstrate that you are who you say you are and that is your public key. The CA is also not required to be online at all times to verify the validity of certificates. So you can actually verify the validity of certificates without having the CA always being online. The CA only needs to be online to distribute certificates. You can check the validity of certificates without the CA, which is a big advantage. So here's just an example of a certificate. It holds the public key right at the top. It holds the name, and it's always signed with the CA's private key. Certificates have other uses as well. We've already discussed that they can be used to identify a principal, which we said a principal is basically a noun: person, place, thing, organization, company, and they're used to bind a public key to that entity. Certificates can also confirm attributes of a principal, so they can verify that you are indeed over the age of 18, that you're a citizen of the United States, that you're male, you have blonde hair, whatever it is. If it can be certified, or if it can be verified, it can be certified. And we're not going to go over the third point here. X509 is the standard for writing certificates as of right now. It's in its simplest form, it's just a way to describe certificates. It tells us what the fields are, how they should be written, and what order they come in, things like that. So here are some of the fields of an X509 certificate. It contains things like the version, the serial number, the issuer, etc., and they're just used to make sure that you can be validated. So we don't have a single CA. We actually have a different system, but we're going to go over some of the problems of a single CA first and show why we need this newer system. So one of the reasons that we don't want a single CA is that one CA would most likely collapse under the heavy load. Imagine one CA providing certificates for the entire world. There's no way it would be able to manage and handle all that demand. Secondly, one organization would be solely responsible for the world's electronic infrastructure. So if this organization were to fall, security as we know it, at least online, would basically be demolished, and we would need to rebuild from the ground up, especially if the private key of the organization were ever discovered. Thirdly, there would likely be disagreement on who would control the single CA. Many people would want maybe the government to control the CA, others would maybe want a private business. And then even if we could decide whether we want a government or private business, it would be a matter of which government or which private business. Many citizens in the US might not trust another country's government to run the CA and vice versa. The answer to this is PKI, and that is public key infrastructure. Public key infrastructure has numerous components, including users, CAs, certificates, and directories, and its main purpose is to define the standards for the various documents and protocols and to basically structure all these other entities. Here's an example of a very common PKI. It's basically a hierarchy where you start at the root. The root and all these boxes are going to be CAs. So the root is your primary CA. The root is then going to hand a certificate to other CAs, in these cases RA, RA1, and RA2, and that in this example just stands for regional authority. RA2s, or RAs in general, are going to distribute certificates to the people below them, which are more CAs. And then finally, these CAs are going to distribute certificates to individuals, companies, etc. So if I ever wanted to verify that Bob is who he says he is, I can ask to see his certificate, and he would show me that he was certified by CA4. CA4, I could go to them, check their certificate, see that they're certified by RA2, and go all the way up the chain back to the root. And then I can make a decision based on my trust for the root. And most of the roots are very well known, and we'll see that in a second. So there are a couple of characteristics of this hierarchy. The first is that everyone is assumed to know the root. And nowadays, modern day browsers will typically actually come preloaded with public keys for over 100 roots, and they're known as trust anchors. A chain of certificates that go back to the root is called a chain of trust or a certification path. So there are a couple ways we could also store these certificates. The first way is that each user can be assigned to store his or her own certificates, but this is rather inconvenient. Two more plausible examples would be the DNS could be used as a certificate directory, allowing certificate chains to be given with IP addresses. So every time you would type in a DNS, you would get an IP address as well as the certificate for that IP address so that you could authenticate it. And then the final way is we could have dedicated directory servers, and they could be used to manage certificates. And these would support functions like searching for a certificate by serial number, name, date, etc., things like that. Basically, think of it as a giant Google search engine for only certificates. Certificates can be revoked. Like I said before, they're much like driver's license, where if a driver drives drunk or if they drive recklessly, a judge can revoke their license. And certificates are no different. If a certificate is abused or its private keys have been leaked, revocation is a very common solution. The way this works is that the CA will actually release a CRL, or a certificate revocation list, and that can be checked, and it will contain all the serial numbers of all the certificates that have been revoked, so that people are up to date on which certificates are valid and which aren't. They also come with expiration dates, so these things don't last forever either. And I think that